Okay, in 9.2, we are studying one of the most basic principles of counting, and that's the multiplication rule. So let's consider the following situation. We're at a coffee shop and we're ready to order a drink, and we look at the menu, pretend that we have this sort of reduced menu. And the question is as follows: how many different possibilities of drinks are there from this menu? Okay, so what we're going to do to answer this question is we're going to count the number of different drinks that you could make from this menu, and the organization of that counting is going to be a possibility tree. So this is how we organize the count. So we sort of draw this diagram, we start over here to the left, and we sort of build the possibilities in 3 different stages. We understand that the drink that we make is going to have a certain type, a certain size, and a certain temperature. So we sort of decide on those qualities in stages. So step number 1 is we're going to decide on the type. And at this stage, I have 3 different choices, apparently, in this reduced menu. I can either have a latte, a mocha, or just plain old brewed coffee. So that's 3 possibilities. Write them here. Okay, and in the second step, I get to decide what size I want to make this drink. So at the moment, I've sort of got 3 options, but within each of those options, I'm going to have 3 different sizes that I could choose, right? I could have a tall latte, grande, or venti latte, or I could have any of those 3 sizes of mocha, or any of those 3 sizes of coffee. So I draw on my, well, first let me label the column here. Step 2 is decide on the size, and we continue growing our tree. So for latte, I'm going to have 3 different options of size, and so on. Okay, let me fill this out. Okay, so as I enter step number 3, I've sort of got 9 situations I could find myself in, and I'm ready to make my last choice, which is step 3, the temperature. And I understand of these 9 situations, I can go one of 2 ways, hot or iced. So let me try and squeeze in those branches. Okay, so here's the point. At the end of drawing this tree, every single node here on the far right represents a distinct drink. So if you follow any one of these branches through the tree, you'll get a distinct drink. So for example, let's follow this one. Let's say I have a mocha that's venti and hot, like that. A coffee that is tall and iced. There are apparently, let's see here, 9 times 2 many nodes over here. So there's 18 distinct drinks. And let's take a look at the math that we used in that counting. I can visualize it and I can just count the dots, but how could I get this answer without having to draw this super awkward tree? Well, at step 1, I had 3 choices, and for each one of those choices, at the second stage, I had 3 possibilities for the type of drink, or no, the size of the drink. So I multiply those 2 to get how many possibilities there are at that stage. And then the very final stage of deciding the temperature, there was only 2 choices, and every single one of the 9 possibilities coming into that stage had a choice of 2 temperatures. So in this way, I get the answer of 18. So this right here is the multiplication principle, and drawing this possibility tree helped us sort of sort out how the multiplication principle was working. All right, let me ask a follow-up question that motivates another principle. What if I went to the same coffee shop and I asked you, let's say they were like handing out drinks at random and each of the drinks was like equally as likely to get made. What's the probability that I got a venti mocha? Okay, so a probability is just like a chance of getting this outcome, and so we give that probability either in a number between 0 and 1 or as a percentage. So let's just think about it. How many different venti mochas are there in this tree? There's a hot venti mocha, Where am I? Right here, yeah. So a hot venti mocha or an iced venti mocha. And all the other drinks are neither venti nor mocha. So what's the probability if someone grabs one of these at random, it's going to be one of those? Well, that's simply going to be the number of venti mochas that there are, which I think is 2, divided by the total number of drinks that there are, which is 18. And this is a very, very common computation when you're thinking about computing probabilities from finite sets like this. If you have a finite number of possible outcomes and you want to know the probability of a specific set of outcomes, you just divide like this. So the answer here is going to be 2 over 18, or 1/9, which is approximately equal to 0.11, so like an 11% chance that you're going to get a venti. Okay, I'm going to motivate another concept of counting with this example. OneNote has this like ridiculous clip art here, so I'm using these images to represent 4 different people: Patty, Nick, Chris, and Tina. And suppose that we ask these 4 people to stand in front of the room and line up in some order. How many different ways could they do that? So how many ways could these people make a line? So like they very well may choose to keep the order that they're presented here. Maybe Patty goes first, then Nick, Chris, and Tina. Well, maybe Tina moves to the front of the line, and it's Tina, then Patty, Nick, and Chris. There's many different arrangements that these 4 people could make, right? Well, let's use the multiplication principle to sort of figure out what the answer is, of course. I'm not going to draw the whole tree because that'll be a mess. Instead, I'm just going to go ahead and sort of sort it out using the same logic. So here's the logic that I'll use. There's going to be 4 places that the people can stand, and I can move from left to right, right to left, however I want to do this, and I can understand it as a sequence of choices. So at the beginning, if nobody has yet lined up, I can understand that there are 4 choices for who can take the front of the line. And by the time someone chooses that position, there's only going to be 3 people left to serve as the second person in line. So there's 3 choices by the time I get here. And then 2 choices, and then 3 choices. Oh, sorry, 1 choice. The last person standing needs to go to the end of the line. And, you know, for every one of the 4 choices, like Patty, Nick, Chris, or Tina, to stand in the front, there's going to be 3 options for second choices. So if I do actually build a possibility tree, it's going to start with 4 branches, then 3 branches going out of each of those, then 2 branches going out of each of those, and then 1 final branch that doesn't really make a difference. But the multiplication principle tells me that the total possible lineups of these 4 people then is 4 times 3 times 2 times 1, which is 24, and that is a number that we've seen before. It's called 4 factorial. Okay, and then this is like a general principle. The number of ways, let me write this in general. So the number of ways to line up n objects is n factorial. Let's ask a different question. Let's suppose now that we're not going to have all 4 of them line up, but we only want to select 2 of them. And let's say that we want to choose 2 of these people to serve as president and vice president of, I don't know, some club or something, right? So supposing I chose Nick and Tina to serve, then maybe Nick would be chosen as the president and Tina would be chosen as the vice president. Or maybe Tina would be the president and Nick was the vice president. So there's sort of, you know, 2 ideas here that I have to take into account. I have to select 2 people and then I have to put them in order. But if I go through the same decision process as I did above, then I get all of that sorted out. So president is going to be put to the left, and vice president is going to be put to the right. And I understand that I simply have 4 choices for who's going to be president, and at that stage I'll only have 3 people left to choose for vice president. So there are 12 ways to select a president and vice president from this group? I forgot to write the question. Okay, what we do when we sort of build these lineups of people where the order matters, what we're doing is we're forming what are called permutations of the objects that were presented. So here we're presented 4 people, and the first question is basically, what are all the length 4 lines that you can make from them? That's just the full number of permutations of these 4 objects. And there's always n factorial many full permutations of n objects. Then the second question was more about take a smaller subcollection of objects and then line them up. The whole president versus vice president thing means that there's some difference. We're not just grabbing 2 people at random, we're grabbing 2 people and then putting them in order. We're putting one as president and one as vice president. That's also called permutation. It's just not the permutation of the full set of objects. It's the number of permutations from 4 objects and selecting 3. So this right here in general is the following. I'll write it out. Okay, so that is the notation for the number of permutations of R objects chosen from N objects. And let me tell you how we can compute this number. Let me just look back to the example and you'll see why it's the case. So 4 times 3 was the answer for here. That was a number of, I meant to say 2 there, sorry. It's a number of permutations of 2 objects chosen from 4. Sorry, I saw the 3 above and got confused. So again, let me clarify what we're doing here. We're selecting 2 objects from 4 and lining them up. That's the number of permutations of 2 objects chosen from 4. And the count here is that I've got 4 choices for the first person and 3 choices for the second person. So 12 is the answer to P42, I guess. Okay, but let me make an observation about the number 12. Notice that 4 times 3 is the same thing as 4 times 3 times 2 times 1 divided by 2 times 1. So if I put a little redundant 2 times 1 in there, I can write 4 times 3 as 4 factorial over 2 factorial. And actually, that's a general formula for PNR. The number of ways, the number of permutations of R objects selected from N.